Hello, I'm James from Team November, and our project was to unlock the graphics power of the Raspberry Pi. So, the Pi has a 700 megahertz ARM processor, and according to our design brief, this reduces its appeal to children because it's just so slow. And I mean, it is pretty slow. I first tried out the Raspberry Pi, and basically, you wouldn't want to move your mouse at the same time as compiling code because, you know, that uses up 20% of the CPU just moving your mouse. So, well, our client from MathWorks was really looking for us to improve the performance of applications that would use Simulink as a toolkit. Simulink allows you to basically create a block diagram with various components in it, linked together by wires, and it's a very easy way to program, particularly useful for maybe some like hobbyist electronics or like high school electronics projects, this sort of thing. So the Pi would easily run into some sort of CPU barrier with a lot of these sorts of projects. So our options for improving this really revolved around making use of the GPU, which is on the same chip, and it has an OpenGL ES2 implementation on top of it, which you can access from the operating system, and that, according to the datasheet, gives you a gigapixel per second fill rate in your fragment shaders, and it's generally a bit more promising than a 700 megahertz ARM processor. So here's a Mandelbrot set generated on the GPU, and it was a few times faster than what you get if you're doing the same thing on the ARM. Unfortunately, OpenGL ES2 is like OpenGL, but basically with all the useful things taken out from our perspective. You can basically have your texture, which is effectively your memory and general purpose uses of the graphics card, and that will only let you have colors which are in small integers, RGBA texture, and then if you're actually using the shaders, you could only work in floating point, and the conversion overhead with no bit shifts or anything is just ridiculous. So basically, we couldn't use OpenGL ES. So fortunately, we were able to bypass that by sort of going a layer underneath and working directly with the native instruction format for the Video Core 4, which is effectively the GPU in the Raspberry Pi. Unfortunately, the firmware is distributed as a binary. It's closed source, and the instruction format wasn't even documented at all at the time. The sort of bad news for us was that, like, literally last Friday, they released a document detailing it. So we had to spend a lot of time reverse engineering it, and it was sort of for nothing, but at least we had fun doing it. Or pain as well, but oh well. So fortunately, what we did have at the time was a fast Fourier transform implementation by someone at Broadcom, which we were able to decompile the shader code for and work out how you could extend that to matrix multiplication and various vector operations. And we also had a mailbox interface in the kernel that let you submit code to the Video Core to run. What we were really targeting is this, well, each one of these is a QPU. That's effectively what runs the shaders. Each one is a SIMD processor. It lets you do 4 32-bit operators on 32-bit floats or ints. And it can actually pipeline that over 4 cycles, so you can get 16 in 4 cycles on each one. You have 4 of these sharing some cache, and you have 3 slices. The documentation basically says that you can use 4, but we found you can use 3. So we basically wrote lots of native code, and we're going to skip back, we don't have that much time, but effectively the memory access latency is quite high, so you want to avoid this for simple operations, but for complicated ones you basically get a huge speed up. Here we have matrix multiplication on large things taking seconds on the ARM and hardly any time on the GPU. So we had to integrate this with Simulink so that we could actually have an easy way of using this and deploying it to your Raspberry Pi. So we basically used an LLVM source-to-source transformation, which we injected in the middle of its build process between the coder and the Raspberry Pi toolkit. And this let us effectively swap out calls to the API that we've written mostly in assembler and their custom language. So to summarize, we basically have sped up some Simulink models with a Raspberry Pi's GPU. And further work would really want to use our work to improve the Raspberry Pi toolkit that MATLAB provides, because unlike all the rest of their code generation stuff, which is pretty mature and works really well, the Raspberry Pi toolkit really lacks a lot of features. For example, this fun FFT wave demo, which uses 2D inverse FFT, which we could easily batch and send to the graphics card in one big go, and it would go really fast. We couldn't actually display it in real time because it lacks some features. So our project really fit in well there for future work. And so thanks for listening.